All right, so are you ready to talk about page 3 of Final Exam Review Part 1? I hope so, because that's what's about to happen. Yeah, page 3 has, 8, 9, 10, 11. So there's 4 problems here. One of them is a couple steps. Some of them are pretty quick, I think. But, let's see what's the situation while I get my computer oriented the right way. Okay, we're good. All right, so question number 8. A toy car is propelled forward from rest by a girl's hand, which causes it to reach forward velocity of 3.5 meters per second in 0.7 seconds. It is then released and later stops in 5.3 seconds. What is the acceleration with which the car speeded up? Well, you know what I'm going to want to do here, right? And if what you said was make a graph that represents the velocity, you are absolutely right. Let's do that. Velocity and time. Okay, so what do we know? So we know it starts from rest, so the initial velocity is 0. The hand, right, kind of pushes it forward, and it jumps up to a velocity of 3.5 meters per second. So it looks like this. And then it's let go, and then the friction or whatever of the floor causes it to slow down at a constant rate. And so the velocity does something like this. So it kind of makes this triangle shape. What do we know about the time part of it? Well, for part 1, t equals 0.7 seconds. And then for part 2, it takes a lot longer. The time is 5.3 seconds, okay? So this graph isn't really to scale, but that's all right. I think we can still make good use of it. Let's knock out part A and part B pretty quick, because that's just using the fact that acceleration equals change in velocity over the change in time. So for part A, if the change in velocity was 3.5 meters per second, and that change occurred in a time of 0.7 seconds, then my acceleration is going to be 3.5 divided by 0.7. Oh, wow, okay. Just 5 meters per second, okay? That's the acceleration for part A. For part B, the acceleration is going to be much slower. It's also negative because we're talking about a negative change in velocity. So here our acceleration is going to be negative 3.5 meters per second divided by 5.3 seconds. So that's 3.5 divided by 5.3. I get it's going to be negative 0.66 meters per second squared, right? So there's part A and part B. Great. Part C, how far did the toy car travel? Well, I can actually find that out just by finding the area of this this velocity graph here, right? I actually know, even though technically we sort of were thinking about it in 2 parts, it's one triangle, right? So the area, which is the distance, is still 1/2 times base times height. What is the height of this? Well, the height of this, the change in velocity was 3.5, and the total time is 0.7 plus 5.3, right? Yeah, which if I add those 2 times together to get the whole base, that's just 6. Great. So altogether what I end up with is D equals, let's see, 1/2 3.5 times 6. 3.5 times 0.5 times 6 is 10.5 meters. All right. All right. So I think then that's a wrap for number 8. Let's take a look at number 9. Where did I put my eraser? Down here. Okay. Number 9. Number 9 is about Josie pulling a wagon with a dog. The mass of the dog and the wagon together is 40 kilograms. Okay, so we're kind of moving on. We're now moving on to another unit. This was the unit on Newton's laws. And I think the law that is applicable here for number 9 is F equals ma, right? Because what we're told is the acceleration is 0.75 meters per second squared. The mass is 40 kilograms. And we're trying to figure out the force. So yeah, this is basically just use F equals ma to figure out the force. Literally just multiplying 40 times 0.75. I can do that by doing 40 times 0.75, and that gives me the force equals 30 newtons. And I think that's it. I think that is it for number 9, okay? So I think we're ready to move on to number 10, which looks like another, I think these next two are actually also Newton's second law kind of questions. So let's see what number 10 is about. Number 10 says, a crate is dragged across an ice-covered lake. The box accelerates at 0.85 meters per second squared and is pulled by a 30 Newton force, okay? What is the mass of the box? Now, one thing I do want to say here is there's this information at the beginning about the fact that it's being dragged, this crate is being dragged over an ice-covered lake. I think what that's meaning to tell us is that there's no friction involved here, okay? All of the force that is being applied to move this box and to get this box to accelerate is strictly going into moving, you know, basically changing the momentum of that box. None of that force is fighting against some friction. So I think that's why it says that, which means all I need to do is use F equals ma. We know force equals 30 newtons. M we don't know, but the acceleration is 0.85. Okay, divide both sides by 0.85, and we're going to get the mass that we're looking for. 30 divided by 0.85 is 35.3 kilograms. Mass equals 35.3 kilograms. All right. And yeah, I think that's it. That's a wrap for number 10. So now we got number 11, and then we are finished going over the first 11 problems from the final exam review. Number 11 says 4 people push a stalled vehicle. Each person pushes with a 250 Newton force. What is the mass of the car if it accelerates at 0.95 meters per second squared? So we've got this car, right? I don't know if there's someone in it or not. Probably someone needs to be steering the car while these 4 people push. So there's 4 people out here. They're all pushing, right, with 250 newtons of force. So the total force total is going to be equal to 250 times 4, which is 1,000 newtons, right? Great. F equals ma. Force equals 1,000. The mass we don't know, but the acceleration is 0.95. So this is setting up exactly the same way as number 10 did. This is number 11. So I just have to divide 1,000 by 0.95, and I get 1,052.6 kilograms. All right. And I think that's it. Okay. So there's the first 11. Hopefully these videos are helpful, allow you to check your work and see where maybe you had to go and fix some things. Or maybe it's the case that you watch these videos and you're still not sure about how to do certain things, which is a good reason to come and talk to me in the virtual class at 2 o'clock today. So I will see you then. Until then, cheers. Enjoy the snow. Enjoy the coffee. And I'll see you soon. Later on.